Welcome to my introduction to trigonometry, slideshow number 1. In these trigonometry slideshows, I'll be showing you just how easy it is to think about and work with trigonometrical ideas like sines, cosines and tangents. It's assumed that you know a little bit about basic geometry and the xy coordinate system. It's also assumed that you know the very basic fact behind Pythagoras' theorem that when you draw squares on the sides of a right triangle, as in this figure, the area of the two smaller squares added together is equal to the area of the larger square. You also need to understand that if you know the area of a square, the length of each of its sides is the square root of that area. If you're not sure about these ideas, learn a bit about them first, then come back to this slideshow. If you continue, remember that this is a video. You can pause it, repeat it, skip back and forth as much as you like. And if you have any questions or comments, you can post them on the YouTube page. Okay, on we go. A point in the xy coordinate plane can be thought of as the intersection of two lines. One line in which every point has a certain x coordinate, and another in which every point has a certain y coordinate. The animated lines here are intersecting where the x and the y coordinates are the same. We're stopping at a special point that is 1 unit from the origin. The point P is at the top of a triangle. The height of the triangle is equal to the y coordinate of point P, and its base is equal to the x coordinate. It is a right isosceles triangle of angles 45 degrees, 90 degrees, and 45 degrees. We can change the x and y coordinates of P, still keeping P 1 unit distant from the origin. The angles of the triangle would change, but we can also think of the angle changing and the x and y coordinates changing because of it. Okay, we've done a full 360 back to our right isosceles triangle. Can we work out what the coordinates of P actually are? Pythagoras' theorem is about right triangles, and that's what we've got, a right triangle. All it says is that the area of the two blue squares added together make the same as the area of the red square. What's the area of the red square? Well, the side is 1 unit, so it's 1 by 1, or 1 square unit. What's the difference between 1 unit and 1 square unit? Isn't that just being picky? No, as we'll see, we have to be clear about when we're talking about lengths and when we're talking about areas. A square with side length 2 has an area of 4, not 2 square units, for example. Anyway, look at the blue squares. The areas of the blue squares add up to the area of the red square, and the two blue squares are the same as each other. So they must each have an area of half a square unit. If you need any convincing, count up the blue and the red triangles. If the area of each blue square is half of a square unit, their side lengths must be the square root of 1/2, because the square root of a half multiplied by the square root of a half is a half. What we've just done is to work out the sine and the cosine of 45 degrees, because the sine of 45 degrees is the very same thing as the y coordinate of P. And the cosine of 45 degrees is the very same thing as its x coordinate. The sine of 45 degrees is equal to the square root of a half, and the cosine of 45 degrees is also equal to the square root of a half. That's for 45 degrees. But watch what happens to the x and y coordinates, the cosines and the sines, when we change the angle. Sometimes they're positive, sometimes 0, and sometimes negative. Don't worry about the actual numbers for now, just watch. So, a quick recap. The cosine of 45 degrees is the x coordinate of P. The sine of 45 degrees is the y coordinate. The areas of the two blue squares add up to the area of the red square. They are half a square unit in area each. So their side lengths are equal to the square root of a half. And this gives us the value of the sine and the cosine of 45 degrees. So what about 60 degrees? Can we work out the sine and cosine of 60 degrees? We're going to use the fact that whatever the angle, the point P always lies on a circle. The circle's radius is 1 and its centre is the origin. Can you see an equilateral triangle here? I guess you've seen a diagram like this before. The vertical line through P cuts an equilateral triangle in half. So the base of the marked right triangle is half a unit. Let's put this information into our Pythagoras diagram. What's a half squared? A half squared is a quarter. A half of a half is a quarter. The smaller blue square is a quarter of the area of the red square. That means that the area of the larger blue square must be 3/4 of the area of the red square. Okay, here's 45 degrees once again. This time we're going to look at other instances of the 45, 90, 45 triangle. We'll rotate the figure. At 135 degrees, the sine is the same, but the cosine is negative. Let's rotate the figure again. At 225 degrees, it's still a 45, 90, 45 triangle, but both the sine and the cosine are negative. At 315 degrees, the cosine is positive and the sine is negative. Here's a record of the sines and cosines of angles that produce a 45, 90, 45 triangle. Note the positive and negative values. Now we'll look at the rotations that produce a 30, 90, 60 triangle. Here's the original one. Let's rotate it. The sine, or y coordinate, hasn't changed, but the cosine, or x coordinate, is negative. Rotating again. The sine and the cosine have traded places, except the cosine stays negative and the sine stays positive. It's the same 30, 90, 60 triangle, but oriented in a different way. Here the sine and cosine values are the same as before, except the sine value has become negative. Sine and cosine trading places again. Same triangle, different orientation. The cosine turns positive. Trade places. And the final one on this round. The sine becomes positive again. Here are all the results, all together in one diagram. It's called the unit circle because of its radius of 1 unit. To work out these results any time, you just have to remember the two types of right-angled triangles we have been looking at. The 45, 90, 45, with its shorter sides, each of length the square root of a half, and the 30, 90, 60 triangle with its shorter sides of the square root of a quarter and the square root of 3/4. Then what you need to do is to find where each type of triangle comes up as you rotate round the unit circle. Some people take the square root of the denominator 4, which of course is 2, and describe the 30, 90, 60 triangle as having shorter sides, 1/2, and a half of root 3. But I prefer the way in this diagram. It reminds us of where the numbers come from Pythagoras' theorem. The squares 1/4 and 3/4 add up to 1. The squares of root half and root half also add up to 1. Try this with a calculator. Take any angle, find its sine and square it. Now find its cosine and square it. Add the two results. What do you get? Why? I hope that you have found this slide presentation interesting. Please look out for the next one in the series.